Sorry?
Ready? Okay. 5, 4, 3, 2, 1, go! Then they go and hunt it, and they find it, and that's it. So marginal relevance, I guess. Actually, it has strong relevance to what we're talking about. Balloons go up because their density is less than the density around them. And really what that results in is a mismatch in the forces that act on the balloon, a net upwards force by buoyancy. And actually that is due to the pressure distribution at the base of the balloon due to the vertical column of the fluid, gas in the balloon, gas outside the balloon, that acts at the base of the balloon. There's a net force pushing it upwards. And so we'll maybe look at that as we go through this. And so that's the relevance of of that particular little ditty, I guess, in this respect. Okay? So we'll follow on from last time. We made the point last time that our interest is in, if we're looking at fluid statics, the pressure at a point, which is what we'd like to get, depends on the fluid pressures around us. And if we recall what we did last time, just recapping, you'll remember that we developed some relationships, I guess, that define behavior. And it might be useful for us just to recall what those were. You might remember that we resolved forces in the vertical direction, which is positive upwards. And we came up with a relationship that said something like the pressure change with elevation multiplied by the density of the fluid times gravity minus the density of the fluid times the acceleration in the z direction is equal to 0. And by inference, we did it in each of the three other directions, and we ended up with expressions which were mere parodies, I guess, or similar images of these, I guess. In the y direction, and in the x direction, we ended up with rate of change of pressure with x minus 0, because gravity only acts vertically upwards. It doesn't act in the horizontal directions. And any acceleration that we apply in that direction. We noted that this really is the same as F minus ma equals 0. With this being the, wish I could do a dotted line, but this being the difference. These are the pressures that are acting, which are forces, either due to the body weight of the fluid in the bucket, the differential bucket, or due to a pressure change with depth. And the point with this is that the fluid pressure at a point relies on not just the behavior at the point, but the column above you. And for us in the sitting below the atmosphere, the column above us is the air that goes up above us, held to the planet by gravity, that stops or peters out as you go into space 100 kilometers above us. But the net consequence of these is that, at least for the case where we have no accelerations, if we ignore these, we'll come back to these later, at least for those cases, there are a couple of things that are important. The first is that this governing equation is always the case. This is always true, and that comes directly from this first expression. And from the other expressions, the other self-evident truth is that pressure changes in the x and in the y directions, and I hope you're making the distinction between pressures and densities, right, are equal to 0. And not apparent from this expression, but also important to us, is that the pressure that acts in the x direction and in the y direction and in the z direction are all equal to each other. Not equal to 0, but all equal to each other. We took this expression here, and I guess we made the point that we can use this in two ways. One is in an incompressible fluid. We said this last time, which is code word, I guess, for a liquid. Then we can write this expression here. We can write it merely as dP is equal to minus unit weight dz. We can integrate both sides if unit weight is constant, and we end up with P is equal to minus gamma z plus a constant. We did it differently. We did it between limits, between points 1 and 2 last time, but this is the same way of doing it without limits. The units of this, from what we said before, have to be a pressure. And so this is just a pressure at some reference location, P0, that we choose. And so the consequence of this is that if we look at pressure distribution with depth, say below the surface of a fluid, then all this says, as we made the point last time, is that this pressure P1 at Z1, we can think of this really, if you like to think of things more simplistically, that the pressure at 1 is equal to the pressure at Z, 0, this one, plus unit weight times h. The negative here is because we choose this. This is the negative minus VE. Minus VE in my shorthand means negative. Plus VE means positive. This is the negative z-axis, so z is positive upwards. But if you choose distances and go down, then the distance down will always give you an increase in pressure. So if you know what this is at atmospheric, if you take it as gauge pressure, it's 0. If you take it as absolute pressure, it's 101 kPa. But if you take this and you know the unit weight of the fluid and you know the depth, then you can get this. And so that's for an incompressible fluid. The application, if you like, for that would be, we didn't see much on the news, but the Hurricane Lane, was it, in Hawaii that just went past? Usually a big deal about hurricanes is the magnitude of the storm surge. And the reason for the storm surge, I guess, is due to partly this second relationship here. And this basically says that as you go horizontally in a fluid, so if we went over in this fluid to some location over here, and we go down, then we'd find out that the pressures at Z1 over here would be exactly the same as it was over here, just moving laterally. So as you go from this point here to this point, if you don't go up or down, so the distance is 0, so you're not going up or down, so there's no change in elevation. And as you go horizontally, there's no net change in pressure as you go horizontally either because of these. Then the pressure at these 2 points have to be the same. And so the importance that, or the relevance, I guess, for storm surge is that, you know, when you expect storm surges, I think for the hurricane, was it Harvey last year in Texas? The storm surge was supposed to be 8 feet, 8 or 10 feet, which is a big number if you're flat. We didn't hear very much about it in Hawaii, maybe because it's a rock that comes out of the Pacific and it's not so flat. And so the storm surge issues aren't so important. More important probably was the 30 inches of rain they got in 12 hours. But because horizontally as you move there should be no pressure change, then the pressure at this point here, which would be atmospheric, has to be the same as you go within the fluid in the middle of the hurricane at this point here. So this has to be equal to this. And so that means that the magnitude of the pressure that's acting on here, the air pressure, has to be less than this air pressure by an amount equal to this height rise of water. And so if you look at hurricanes, where we sit here at 1 atmosphere, we are at something like 1,000 millibars of that order. If you look at the deepest low pressure within the middle of a hurricane, it's something like 800-ish millibars. So the difference is about 100 millibars. And this is equal to, say, 100 kPa. So 100 millibars is equal to 10 kPa. Then, if you wanted to, you could work out that this height here has to equal the density of water times gravity, or rather the pressure. The pressure has to equal this. And so, if we know the magnitude of the pressure is something like 10 kPa, we know that density of water is 100,000 kilograms per meter cubed. Gravity is 10 meters per second squared times h. This term here is exactly 10 kilonewtons, as if you work it out. So it's 1,000 times 10, which is 10 to the 4, 10 to the 4 newtons per meter squared. So this height has to be equal to 1 meter. So you could calculate what the magnitude of the storm surge would be just based on atmospheric pressures between the outside of the storm and the inside of the storm where it's extreme low pressure. And you could figure out that if you have a storm surge of 10 feet, 3 meters, then it's not all due to the pressure differential. Part of it's due to the water being pushed on land by the wind. Okay? So we got diverted a little bit. So the second part is if we look at a compressible fluid, as we did last time, then we can do the same as we did before. We find out that for compressible fluid, we do exactly the same thing as before, but now, unfortunately, or not unfortunately, rho g is not constant, and we know from the ideal gas law that pressure is equal to density times universal gas constant divided by the weight of the gas times temperature. If we rearrange those in terms of density, then we see that this density is a function of pressure multiplied by mass and divided by RT. We made the point that now when you substitute this, you get a slightly different equation. But the point I guess I was going to make, which I don't have too much room for, comes back to our hot air balloon. Actually, it wasn't a hot air balloon, right? You saw them, if you came in early enough, you saw them putting gas in it. I presume helium or hydrogen, probably helium. So if you look at the pressure differential, if this little square is our balloon, and if you look at the pressure within that balloon, you'd see that it varies with something with depth and pressure. And if you look at the pressure outside the balloon along its side, since the density is larger, then the change in pressure as you go down through the column alongside the balloon is offset. And so this means that the pressure that's acting on the base of the balloon from inside is equal to this amount, P in, if you can see that. And the pressure that's acting outside the balloon, upwards, is P out. And if you look at reconciling these two, by definition, the red one has to be larger. If the red one's larger, then there is a net force that's acting upwards. And we know from F equals ma, if there's a force acting outwards that isn't balanced, then it accelerates. And accelerates depending on the mass of the balloon. And so that's the mechanism by which a balloon rises. So it rises because the density inside is less, and the mechanisms by which that density can be less is really governed by the ideal gas law. It can either be hotter inside, a hot air balloon, which isn't sealed, it's just heated, as you know. So if temperature is larger, the density inside is less. You could, this is a constant, but you could use a gas that has a lower molecular weight and therefore is less dense than the air around it. So using helium instead of the nitrogen in the air around us, nitrogen-oxygen mixture, mainly nitrogen. Or you can try and use a lower pressure in the balloon. It's almost impossible to have a lower pressure in the balloon because the balloon is just a membrane. And if you have a lower pressure in the balloon, it just collapses to that size. And so the mechanisms by which a balloon work are really governed by this. But the physical mechanism by which it moves upwards is by buoyancy, which we'll talk about later, I guess, in 3.3, I think, to be able to deal with that. Okay? So that's our recap, I guess, and putting it maybe in context. So what we got out of last time was this, which we can use for an incompressible fluid or a compressible fluid. The fact that as we go horizontally in a fluid, pressures don't change laterally, and the pressure at a point is uniform, acting in all directions. What I want to do is come back to the case of a compressible fluid that we talked about last time. And so we made the point last time that in a compressible fluid, we have to do a little bit of integration and we get a relationship. Let's go back to that briefly. And then we'll spend the rest of the day talking about how we measure pressures, specifically using manometry and using these rules that govern exactly what goes on. Right? Okay. So, well, this is it. There are lots of derivations last time. This is what we ended up with last time for the pressure that happens in a column. If we wanted to do that, we could also note that in the derivation of this expression, if we look at the derivation, you remember that we just took this expression here. We noted that density changes with pressure, and therefore we have to use the ideal gas law. We did some substitutions, and after the integration, we ended up with this relationship here. We made the assumption that temperature is always constant and doesn't change. And if we wanted to, I guess we could keep that inside the integral. And then, if that's the case, we could do the integration. So not to belabor the point and not to derive it again, if you look at the temperatures in the atmosphere above us, standard pressure and temperature is at 15 degrees centigrade, which is this, 15. Whoops, didn't mean to do that. And as you go up, you know that if you fly in a plane and you look at the stuff in front of you, it'll tell you it's minus 60 degrees when you're at 30,000 feet or so, which is about 35,000 feet, I guess would be about 10 kilometers. And so what you can do is you can do this integration that includes the temperature as a variable. And if you do that, you get a slightly different relationship from the one we got before, in that now the temperature is a function of elevation. And this is the expression that defines this, if you treat this as a variable. This is the temperature in terms of absolute temperature at the reference location, which is here, which is 15 degrees centigrade. The rate of change of temperature as you go up in the atmosphere is given by this term beta. So we need a value of beta to do that. If we want to get it from this, we know that as we go up 10 to the 4 meters, is that right? 10 kilometers is 10 to the 4 meters. That the temperature changes from 15 to minus 60. So this is minus 75 degrees centigrade, which is also minus 75 Kelvin. You remember that temperatures really have to be in Kelvin because we're using the ideal gas law. So these have to be absolute pressures. These have to be absolute pressures and absolute temperatures because they're part of that gas law. So to be able to get this to go to the right magnitude, this has to be 75 degrees centigrade. The units of this have to be temperature. This is elevation. So temperature is equal to temperature minus elevation, which is in meters. And so to get temperature, we need temperature change over change in elevation, right? the units of this are going to be temperature. So this beta term must be that differential, and so delta T over M, or delta M, is going to be equal to minus 75 divided by 10,000, which I think is 0.0075, right? 1, 2, 0. An extra 0 maybe. 3075. And the units have to be in Kelvin per meter, right? K per meter, degrees centigrade per meter. And so if we use that, we can use that to calculate how far off our results are if we now incorporate temperature. And so I made a little routine. Let's look at that routine. You perhaps can't see that. Let me run it, and then let's look at both the run portion. Yeah. See if it pops up. Yeah, it does. Let me zoom in. So you see this routine. So the pressure at ground surface is 100 kilopascals, 10 to the 5 pascals. Elevation 0, gravity. The temperature at the ground surface is 273, which is 0 Celsius plus 15 degrees. This is the gas constant for air. This is G, again, don't know why it's there twice. And beta is this, oh yeah, I guess it's 75 divided by 10,000, which is 0.007, not 0.0007, right? And this is the rate of change of temperature with elevation. 75 10,000ths per meter. And if you use the expression where we don't correct for temperature and the one where we do correct for temperature, you get these two different curves. Whoops. Doesn't. I'm going to zoom back out again because it's not doing what I wanted to do. So what happened to our curve? Oh, jeez. Let me run it again. Okay. See if I can make that large without zooming in on this. So it's in a little bit of a strange orientation. On the bottom, you have sea level to 10 kilometers. At sea level, we're at 101 kPa, actually 100 in this expression. And as we go up, we get progressively lower and lower pressure. So by the time we get up to 10 kilometers, for the uncorrected case, we are at 30 kilopascals. This is 100, 90, 80, 30 kilopascals. And if we use the correction for temperature, then we're at a magnitude which is slightly different. There may be off by 10% maybe on this. It's perhaps a bit deceiving, but they're not off by very much. So assuming that temperature is constant as we go up in the atmosphere doesn't make much of a difference to us, and so we can get that. So we might want to be able to look at the way pressures change with elevation. Okay. So one way in which we know that the magnitude of pressure at sea level is 101 centigrade, 101 pascals, kilopascals rather, is by using manometry. So the other thing that we'll talk about today, which we'll come back to, is how we can use manometry to get that. We'll go back to our favorite friend. I think we've seen this briefly.
I'm going to make a barometer. And what I have here is a glass tube that's about 800 millimeters long. And I've filled it with mercury. We're going to make a barometer. And what I have here is a glass tube that's about 800 millimeters long. And I've filled it with mercury almost to the top.
800 millimeters.
And I'm going to finish filling it so that I get filled all the way to the very top. And then I'm going to put my finger over the end and I'm going to invert it into the mercury. I'm going to set it here and use our clamp to hold it. Now, what's keeping this mercury column so high? It's that atmospheric pressure pushing down on the mercury, pushing this up. And let's see how tall our column is. 744 millimeters. It doesn't matter what size the diameter of our tube is, as long as it's relatively small. You can see this one's really small. I have another one that's almost twice the diameter of this one.
I can barely hear it.
You can see that the level is the same in both tubes. What we're going to do is compare this crooked barometer to the barometer that we already have. And notice it rises to the same level.
All right. Stop it. Okay. Making a barometer. All right. So we'll the rest of the class, and actually on the following class, we'll talk about measuring fluid pressures in some way. And so we refer to that as manometry. I guess the two important things from what we just saw was that she mentioned, one, that the height doesn't change with the diameter of the tube, but the tube has to be relatively small. Doesn't matter if it's crooked, but relatively small. Of course, relatively small means that you have to be able to sustain a meniscus across it due to surface tension, so it doesn't just collapse. And so that's the reason for that. But what we'll do is we'll maybe look at the rules of manometry. And the rules of manometry are written out here in shorthand, but I'll go through them. They're written down somewhere in the notes, and maybe we'll go through them more fully, and then come back to the manometer question and try and figure out exactly what the physics are that allow us to be able to get why that elevation within the tube is always constant, irrespective of the tube diameter, and then how it measures the pressure around us. This came up in an email question, so maybe it's worth revisiting again, and that is the role of absolute and gauge pressures. So absolute pressure is measured relative to absolute zero, the vacuum in space. And so we sit at 101 kPa, which is due to the weight of air above us as it goes into space. And so if we define that as an atmospheric pressure, this is the magnitude as an atmospheric pressure. This is equal to 0 gauge pressure. If we go to some pressure above that, then from 0 to whatever the pressure is the new gauge pressure. And the absolute pressure would be the gauge pressure plus the magnitude of atmospheric pressure added on top of it. So you need to remember that. You need to remember also that when we talk about the ideal gas law, always pressures and temperatures are absolute, have to be. So you need to remember that. So what we can do is we can look at manometry, but let's look at the rules of manometry, and they're spelled out here, and they're written in shorthand in that one line on the previous text. And that is, what we'll do is we'll work our way through a system, and there's some rules that we can follow that make it a recipe. When we go down in a fluid, then the pressure goes up. Pressure increases as you go down. As you go up in a fluid, the pressure decreases. So that's the first two rules of manometry. Depending on how you do your calculations in gauge pressure or atmospheric pressure, you can do it in either way. You just have to be consistent and use it in gauge or atmospheric pressure all the way through, because if you work through the system, you have to use that. If a vessel's closed, like the barometer, the manometer turned upside down, the pressure in the airspace or the vapor space will be the vapor pressure of whatever that fluid is. And because the density of a gas is much less than the density of a liquid, we usually take the density of a gas as equal to 0. In which case, we can move through gases without making any correction for the elevation change. So those are the rules. You can refer to them. They're exactly the same rules that are written in this one line here. If I go back to it. As you go up, you subtract pressures. As you go down, you add pressures. The pressures horizontally, as you move from the same location, are the same. The vapor pressure acts if the system is evacuated, and the density of a gas is so small that as you go up and down, typically, if there are liquids in the system, you don't have to worry about it. So those are those 5 rules put in one location. So coming back to Vilma with the manometer, the mechanism by which it works is basically this. We can use the expression that we've got before. You remember that this expression comes from this, right? Manipulating this gives us this expression for incompressible fluids, which are liquids. And so what we can do is we can work our way through this system to be able to figure out exactly what the pressure is at some location. We have to choose the place where we don't know. If it's mercury, and we know the vapor pressure of mercury, which we do actually, I looked it up on my phone while we were looking at the thing. The vapor pressure of mercury at roughly room temperature is 1 Pascal, 1 Newton per meter squared. So we know this. And so what we'd like to know is what the pressure is that's around us. And so what we can do is we can use the manometer equation. And so the manometer equation, we'll use this throughout. Don't worry about the rest of the wording on this page. We'll take the pressure at point A. And what we'll do is we'll just work our way through the system to get ultimately to the place that we want to define the pressure. And so the pressure at point A, we're going to go down some height h to this point here. We're going down in the fluid, so the pressure is going to go up. To this point here. And we know that the pressure at this point here, because it's on the same horizontal line at this point, has to equal the pressure at B. B is the barometric pressure, right? And so if we know what this is, and we know what this is, and we know what this is, we could calculate what the barometric pressure is. That would be the right way to do it. We know that this height here has to be 74 centimeters. We got that from the video clip. Or we could do it the other way around. We could figure out exactly what the height should be, given that we know what the barometric pressure is. We know that the barometric pressure should be something like 101 kilopascals. And so we could rearrange this to get that. I'm going to do it in a different color. So in other words, what would it be? It would be PA. No, sorry, just do it the other way around. PB minus PA is equal to H divided by unit weight of mercury. Basically. So, happily for mercury, this number here is basically 0, right? This is 1 Pascal. This is 101 kilopascals. So 10 to the 5 times bigger. So we don't need to do this. So if you look at the ratio of this, it's going to be something like 100. Well, let's just do it properly. Is it 101.3 times 10 to the 3 newtons per meter squared? divided by the density of mercury multiplied through by gravity. So gravity is 9.81. And it turns out that the density of mercury is 130,000 kilograms per cubic meter. So meters per second squared times kilograms gives you newtons, and so the result will be, we should be able to, if you do the calculation, it should come out to be something like 74 centimeters. So 100 divided by 0.3 is a factor of 7 in there somewhere, and it's just the magnitude of this. And so in this particular case, this is so small, that's desirable, because it just basically makes this only one number in the numerator, and it's just the ratio of those two. And so that's how we know that the magnitude of the pressure at sea level is something like 74 centimeters of mercury, which is something like 29 inches of mercury if you do the computation, right? So we can always do this, that we work through the system. So if we have different columns, we can do exactly the same thing. This happens to be that the pressure that we get here, that we've used, this pressure is going to be in absolute pressure, right? All of these pressures, including the vapor pressure, were in absolute pressures. If we want to do an example where it's in gauge pressure, then a typical way to measure behavior, the pressure at a point in the subsurface, is to measure the height of a column of liquid at that point. All the diagrams that you'll look at in your book are these bulbs. They're not bulbs, they're supposed to be pipes going into the page. But if we want to calculate the pressure at a point at PA, then we do exactly the same. We start off at this point here, and we say P0. We go down from this point to this point here, and we do that by subtracting, or adding rather, the unit weight, the density of the liquid, say water, multiplied by H1, and that is equal to PA. If we do it in gauge pressure, then by definition, this is atmospheric pressure in terms of gauge pressure, which is 0. And if we know the density of water, and we know the height, and I'm missing one term here, right? This is gravity. So in other words, we could also write this as P0 plus unit weight of water times H1 is equal to PA. Then the only term that we don't know here is this. We know the unit weight of water. It's what's the unit weight of water? It's 9.81 kilonewtons per meter cubed. 10 roughly, right? So 1,000 kilograms times 9.81 meters per second squared multiplied by the height, and this term still is 0. Okay? So those are the simplest cases. If we have a more complex system, then we can also do the same. Again, this bulb is not a bulb, it's a pipe going into the page. If we want to calculate the pressure in this pipe, then we can do it with a U-tube manometer. Typically, the liquid in the pipe would spill over into part of the manometer tube, but the U-bend of the tube would be closed with a gauge fluid. The gauge fluid has to be different from the fluid, and it's desirable if it's immiscible, that they don't mix in some way. Hence, mercury is a good choice. And of course, mercury is a good choice. I guess we didn't say it when we talked about the barometer. If instead of using mercury, which has a very high density, we used water, we could calculate exactly what the height of water would have to be in that column. If you do the calculation, it'll come out to 20, 25, or 30 feet. And so if you have a barometer that uses water as the gauge fluid, the height of the column has to be much higher than mercury because the density of water is much lower. And so it scales with the density of the fluid that's present there. So if we wanted to calculate the pressure at point A, the easiest way to do it is to just work from this point here. So we write down the pressure at point 4, which is atmospheric. We go down to a point here, which is, we're going down. So we go H2 multiplied by the unit weight of the gauge fluid, which is this. So the pressure increases from this to this magnitude here. We know that we can go from this point within the pipe all the way through to this point without changing elevation. So the pressure here has to be exactly the same pressure as this point here. And then we can go up to point A by going up through this other fluid. We're going up, and so we subtract, which is H1 multiplied by unit weight of fluid A. And that is equal to the pressure at point A. The pressure we probably want is this magnitude here, and we have it arranged directly in that form. If we're working in gauge pressures, then this is 0 gauge. We know the unit weight of the gauge fluid. If this is mercury, we know what it is. We know what this height is. We know what the fluid is that's in the pipe, and so we know this fluid also. We know each of these lengths, and we know, and the only unknown is equal to this. And so that allows us to get the pressure at a point that is not the point where we're sitting at, always in reference to another location. And so it comes out to be this equation down here. So the other quirk on this would be that if this fluid here were a gas, if rho, well, we did it as A. If unit weight A was a gas, then this basically goes to 0. And if this goes to 0, then this term here would be 0, this term here would be 0, and we can do the calculation merely as a function of the difference in elevation between the two levels of the gauge fluid, which is typically what's the case. So if you're measuring pressures in gases, then this differential pressure is just the height of this column between these two legs. Because this pressure here has to be higher than this pressure, and this pressure here represents the pressure in here, this means that the pressure in the pipe is larger than atmospheric pressure, because it's pushing this pressure up on the outside. If it were the other way, then the pressure within the pipe would be depressed relative to atmospheric pressure. Say if the gauge fluid was down here and up here, then this would be the difference in pressure, and this would be an under pressure, not an over pressure. And so you might want to get some feel for those things, right? And so it's really just a recipe in using these rules. So we've gone up, we've gone down, we've talked about gauge pressure and absolute pressure, we've done the barometer with vapor pressure, and we've talked about the gas being of negligible density. You probably can never do too many of these things. We'll spend tomorrow doing some more. This is just more the same as the one we've just done. Let's do this one with the differential manometer, inclined manometer. And so we've made the point that the difference in pressures between the tube and atmospheric pressure, if we're measuring that, or between two tubes, in this case, a pipe going in one direction, a pipe going in the other direction. If there are different pressures, we might like to measure the differential pressure between them. If they're very close pressures to each other, we'd expect that the gauge fluid elevation in the two arms of the U-tube would be very close to each other, and that we can't perhaps make a differential guess as to what the difference between them is. One way to resolve that is to use what we think of as an inclined tube manometer. And the idea is pretty simple, is that instead of looking at a U-tube that would have the shape like this, like a U, in which case the elevation here and the elevation here may be barely discernible from each other because of a small difference in the heights. What we could do is we could stretch out this tube at the base so that it looks along like this. And now we measure the same height in this tube as the pressure here, but by measuring along the tube, the length of the tube to this upper meniscus, which represents the new pressure, we just get the magnitude directly from that. And really all it is a function of trigonometry. This would be the difference in pressure that we have here. So this is the delta H that we want. But delta H is going to be equal to L2 times sine theta, right? So if you know what the inclination of this tube is, bless you, then you can arrange it. If it was vertical, it'd be just like a normal U-tube manometer, right? This would be the vertical leg of the U-tube manometer is vertical. If it's horizontal, it won't quite work, but if it's inclined at some kind of optimum angle, then this term that represents the difference between, I guess, this height here, delta H, which is here, times the gauge fluid, is just identified in terms of this extended term. So instead of trying to measure a small amount here, we measure a longer length here along the tube. And if we know what the inclination of the tube is, we come up with the same calculation. That's it. Okay, I think that's really was almost all I want to say. There are a number of ways to measure pressures using Bourdon gauges, which work with a gas-filled tube that expands as the pressure changes, manometer, and membranes and pressure transducers. If you look at the book, you can see what those are. They're not so important.